Okay, Steph, we've got quite a few people in now, if you'd like to start.
No problem, thank you.
Thank you.
Good morning, everyone, and welcome to the first in the series of our Net Zero webinars. So today's one is there a better way to make that? Today we have three fantastic speakers. So we have Evgenia Yakushina, we have May Hicks, and we have Sampan Seth. All of which reside within an NMIS specialist centre, either within NMIS or the AFRC. Just a little bit of housekeeping to get started. So the webinar is being recorded and it'll be made available on the YouTube channel if you don't manage to catch it all today. So your microphones and your webcams will be turned off during the session just to avoid any background noise. There is a Q&A function and a chat tool, so you can use both during the session. We would encourage you, if you have actual questions for the panel, please use the Q&A box. There will be time allocated at the end for the speakers to answer any of the questions that you may have. And if you wish to follow us on Twitter, you can use the hashtag NMISInsights, and the Twitter handle is @NMISGroup. And at the end of the webinar, you may be asked to complete a survey, so please take some time to do so. For those of you who don't know who we are the National Manufacturing Institute Scotland, and we are a group of industry-led manufacturing research and development facilities. And this is where research, industry and public sector work come together to transform skills and productivity and innovation. Hopefully NMIS will increase the productivity by reducing the barriers to innovation, stimulate investment and increase the manufacturing competitiveness, catalyse job creation within Scotland and strengthen supply chain links globally, inspire and attract talent and equip the current and the future workforces with the skills that they need and that their businesses need. And we also work with manufacturing businesses of all sizes across various different sectors. We are supported by the One Scotland team. We are operated by the University of Strathclyde in Glasgow, and we're supported by several stakeholders and partners, as you can see there on the right-hand side. NMIS as a group, as you can see, I won't go into much detail about that, but we do have currently opened and live just now 2 specialist centres, of which one I'm sitting in just now, the Advanced Forming Research Centre and the Lightweight Manufacturing Centre at the Westway in Renfrew. The core elements of NMIS will involve a digital factory, a collaboration hub and a manufacturing skills academy. You can always reach out if you want any more information regarding the NMIS group. That's all from me, and I will hand over to our first speaker, Evgenia Yakushina. Evgenia.
Thank you very much, Steph. If you can let me know that you can see my screen perfectly.
Yes.
It started from the very end. Is it the same like I see it?
Yeah, you need to go back to the start.
Yeah, great. That's the proper start. All right, good morning, everyone. My name is Evgenia Yakushina. I'm a Senior Knowledge Exchange Fellow in the Advanced Forming Research Center, and I'm the Forming Team Lead as well. Before we will start jumping into the questions, how we can make it better, which is the subject of today's webinar, I would like to share with you what is actually our vision, which is driving us every day to make the things better. As you can see, we have a few sound words, which has been a reflection of the customers' inquiries, our vision, and how we can mitigate these 2 aspects together. So we are really open to pursue innovation in the industry, and actually we are aiming to provoke technology creation, to adapt it, and adaptation is another factor, which is a substantial part of our vision. We are aiming to create environmental, engineering and business impact in the manufacturing industry. So it gives you a bit of an overview how we are seeing ourselves and how we are pursuing our collaboration with industrial and academic sectors. A few words about who we are. Forming Team is one of the oldest team in the Advanced Forming Research Center, and we have a really broad mixture of the senior manufacturing engineers, manufacturing engineers, modelers, R&D, system integration, and the beauty of the team is that It is supported by the people who are PhD awarded, so they've got really deep academic backgrounds. But at the same time, we have people who came directly from industry. So this beautiful combination actually allows us to understand what are the exact requirements from the customer and provide very good hybrid and mixed approach to the inquiries. But before we will be jumping to the subject, I would like that everyone will ask ourselves, why do we need to make it better? And there are, excuse me, there are a few factors which is actually could be easily found on the public domain. But to remind ourselves that we need to remember that actually industry now accounts almost a third of the global final energy use, and it is almost 40% of the total energy which is related to CO2 emissions. We are working for the industry support. We are developing technologies which will, in the next 10 or 15 or 20 years, will be in the industry. And now we need to develop it and optimize it in the way with the understanding what it will be the reflection for our nature. The large portion of the energy consumption in the manufacturing sectors, it is obviously the manufacturing and production processes. So the questions like, what is the energy saving potential? How we can optimize it and look at this from the global warming point of view? How we can work with the reduction of the gas emission? That's the major technological and economical issues which is under discussion right now, and which now should be accounted and embedded into our life. Just to give you a very quick and simple example, not speaking what is the overall CO2 emission for the fancy manufacturing process for the stamping, which is working for the automotive industry 24/7. That's a very simple example. The aluminium disc 6000 series with the dimensions of 6 millimeter by 30 millimeters. So that's something like a stack of two penny coins. For the cold forging, which is the optimized process from the temperature point of view, the total emission of this, it is already 136 grams. If we'll scale it up to the aerospace or the automotive components, which is a square meter, which is 2 square meters, you can imagine what it will be magnification from that size of the coin to the bigger one. And another factor, which is obviously speaking about the Industrial Revolution, is on the screen as well. So if you could imagine that in the 18th century, we have a musket which contains 10 parts only. Now, or actually in the 2000s, we've been speaking about the 747, which contains 10 millions of the parts, and this progression keeps growing. So this is the motivation. Why do we need to make it better and not even start, but actually do it right now? And to update you or give you the flavor of how and what we do in the forming team to make it better. As you can see, the forming team is comprised by the 4 themes, and we are covering the really broad range and variety of all forming process. This is related to the hot or cold sheet forming. Obviously, the tribology, coating, and friction questions are considered as well. And the most efficient procedure is a process modeling. With regards to the particular steps, what we are doing, we work in the very different strategies and direction. So either it is improvements of the current manufacturing process, which will be then embedded to the supply chain effectiveness. We also work in parallel directions, so explore the new opportunities from the innovation. And this opportunity actually bring us to the next level, how we can link the state-of-the-art manufacturing technologies to the business challenges, to the product challenges. And through that, we are facilitating, we are planning and delivering manufacturing technology. But obviously, the very last step and the very important step is how we can de-risk investments in the technology and how this could be implemented to the supply chain. So the next question starting from why, what, how we can make it better. And that's a quite developed, very classical, but very proven scheme, I would say. First of all, it is understanding of the material. There are different types of inquiries which is coming from the customers. Either they would like to optimize the current products and current material, or they would like to implement the new one, or nowadays, they are all asking how I can have the stronger material or how I can make my part lighter. So all this brings us to the very first stage where the material characterized and embed this information into finite element modeling. But we are always saying we need to understand what are the requirements for your tool process. We have a brilliant example where a customer came to us with a hot forming inquiry, says, yes, I would like to form this part at the highest temperature and I will have brilliant formability. That's right, but what will going to happen with your tool? After 100 parts, the tool will deteriorate and you will need to have another one, expensive one, and manufacture it from the very beginning. So this is the place where we're saying we need to understand and bring this understanding for you about the tool and about the manufacturing process. And the final stage is optimization. When you're clear about your material selection, when you know what is your tool and how you can optimize and what will be your process, that's a brilliant opportunity through the modeling, through some different assessment exercises to optimize it. And that's where we could either walk through the line with our manufacturing engineers and pick up every single stage which could be optimized or which need to be validated, or the quality need to be more or improved. And in parallel, we could assess what other alternative manufacturing options could be that we can make it better. Another very important part of my presentation will be dedicated to the unique methodology that have been developed in the forming team of Advanced Forming Research Center. And it is actually about manufacturing process down selection. At the next slide, you can see it's very simplified, but I like when simple templates and the concepts bring it up to the attention, because it led us to start from the very good questions and then dig it out to the very fine level, which is required by the customers or by the challenge itself. So for us, it doesn't matter where we need to start. Some customers are coming to us with brilliant ideas and saying, this is the sketch of the part which I would like you will develop the full manufacturing process, and it will be a turnkey solution. And that's fine. Either it is an inquiry that I would like to have a new design of the part. So it is either the part optimization, or you've got the new features and then thinking about the process that could manufacture this advanced design. Or the nowadays requirement is a stronger material. I would like that material will be stronger. I would like that material will be formable at the same time and lighter. That's a brilliant combination, which is really challenging from the material science point of view. But all this actually targeted to one question: how we can develop the optimized manufacturing technology and make the overall concept better. And the process is named methods of manufacture assessment. So there are 5 main steps which need to be undertaken on the high level, which actually bring you to the stage where you will understand what is the optimal manufacturing processes parameters and how we can make it. So let me guide you through these stages. First of all is assessment of the inquiry, and I spent a bit of time into description how the assessment could be performed. Either it needs to start from the material down selection, and sometimes we have a very developed matrix of the 20 different elements that could be considered as an option. And then we are down selecting with regards to the criteria from the customer. And that brings us to the second step. And the second step is actually about identification of the criteria and weighting. So the customer basically saying us, I would like to have for this part increased manufacturing volume, or I would like that the new features will be added to the same part and material will be stronger. So I need to know what will be the strengthening, what will be the wearability, what will be the bendability, what will be the friction parameters, how the fatigue life, whatever will be the main driver for the customer. And then we are asking, could you please tell us what is the most important for you? And then through the ranking, we could assess all the materials and all the processes as well. So as soon as these 2 steps are performed, we are in the very good position that we could speak about the manufacturing processes itself. And then from the whole variety, from the selection of the manufacturing process, we can rank them and identify who will be the champion. Usually we are selecting 2 or 3 of them and saying that these are the viable options, taking into account your criteria, the weighting parameters, the material that have been down selected. And the final and very important step is assessment of the risk, cost, and effort. Because actually the manufacturing technology could be brilliant. It will form you the part ideally. The quality of the part will be consistent. but the cost of the part will be the criteria which wouldn't let you go for this option, for this manufacturing route. And therefore, the final stage is actually telling you that if you're going for the optimized manufacturing procedure, such as such, you need to manufacture 1,000 pounds in the month. Otherwise, the part will be almost like the cost of the gold. And that's very important to understand all these risks and costs and effort which will be required from the customer or from the supply chain that need to support the manufacturing process. So this was the, let's say, theoretical introduction part, but let me show you on the case studies how we are doing this, how we are making it better. The next few case studies will be from our very own tier 1 partner, Rolls-Royce. And obviously, we've been working on the very high efficient process, not very high efficient, but very resource requiring process, the superplastic forming. It is known that this process used to manufacture hollow white core fan blades, particularly for aerospace jet engines. And that's not a secret for anyone that it is long, it is hot, and it is expensive. And Rolls-Royce came us with inquiry whether there are any opportunities how we can optimize this process. Either we need to put another SPF press in order to increase the manufacturing capabilities, or there are other ways. So what AFRC did, we actually worked on extensive data mining for many years of the Rolls-Royce manufacturing data. So we went through all the data analysis within the AFRC being implemented for the at the Rolls-Royce manufacturing facilities. Then we analyzed the SPF cycles across the multiple stages. So that's almost exactly like we are seeing. We will go through the light. We will go through every single step of the process. And then we developed a novel temperature measurement instruments. Therefore, at the end, we have a brilliant achievement. Actually, the direct result of the project was that new SPF inflation curve with a 27% reduction in cycle time was identified. And then it was validated in the production trials with the Rolls-Royce facilities. So that was a very good result. The project completion research results have been fully implemented at the Rolls-Royce manufacturing process for the fan blades with a minimal disruption to the production. And that's what the main goal and aim of the AFRC, that we can do it better in our facilities using our capabilities or our supply chain capabilities, that it will not disrupt the manufacturing production lines for our customers, and they could bring the ready solution, the ready and validated solution to their lines. The next one example is again how we make it better for the Rolls-Royce, and that's about another side of the SPF process. Obviously, the protection coating is a must thing, and the boron nitride is a water-based coating which is commonly used to provide lubrication for the superplastic form processes. Usually, it's being applied manually, and you can imagine what could be the variability depending on the operator, depending what will be the condition of the humidity, how much it will be put, and so on and so forth. And what does it mean? That this variability will influence on the part quality, on the die wear, and sometimes it could be even die refurbishing and part post-processing as well. Therefore, Rolls-Royce came to us and asked how it could be optimized, how we can make the quality better and a bit more systematic. And therefore, engineers at the AFRC developed the automated spraying facilities, very delicate and efficient at the same time, which allows us to improve the die life, reduce the costs, which obviously will tell us that we do not need any post-processing and potential waste of the material, and the dies, which are substantial costs for the tool and for the SPF, could live longer. Brilliant results. Rolls-Royce was happy, and we are as well. The hydroforming. This is the technology which I will be talking about for the next couple of slides. And again, it was a brilliant example that has been performed in the cooperation with Rolls-Royce. The hydroforming technology is usually, it is a manufacturing process where high pressure hydraulic fluids is used to form the material. And usually it it is applied for the manufacturing and the forming of the low-strength steel and alloy parts. But what was the challenge for us that Rolls-Royce put in front of us? It was how we can challenge the hydroforming technology versus superplastic forming. Is it the economical and financial benefits of it, and how it could be used for the forming of the complex shape parts? So what we did in the AFRC, at the first stage, we obviously go through the cost modeling technique, which is one of the services that have been explored in the forming team. And the modeling technique compare what is the hydroforming against the existing methods of manufacturing. As soon as it was proved, we went for the material characterization data and then generated the final elements model. And then as soon as model developed to represent the hydroforming process, we aid to manufacture the parts and go for the trials. This helps us to validate the model, the physical process that has been carried out. And we've been able to produce defect-free parts with the challenging geometry features and foam. So that was the whole process, how we started from the simple question, can this forming technology actually can be used as an alternative? So can we make the technology better to manufacture the complex shape parts? The next one example, again about the hydroforming, but that's another overview. We've been speaking about the strong parts, but as I said, customers now driven by the very sound word, which is lightweighting. So we start looking, can this technology actually support the light materials? And we've been working on the hydroforming of magnesium. And it was the proof that it could be called as a cost-saving technology. So what we did in this study, the cost comparison showed up to 40% of the cost savings that could be made to produce this complex shape components. And the picture of the components on the left-hand side of the slide, you can see that it comprised a lot of features, radii, the central one, and it was perfectly full, damage-free, and the quality was quite satisfactory. And again, it was a way how we can make it better comparing to the very resource and efficient technology from the point of view of the comparison to the hydroforming. The next one of my favorite case studies, that's a relatively new story for the AFRC about the collaboration with the SME called Crudes Renewables. The main aim and the main objective of this study was about manufacturing of the small-scale water wheel that will work on the waterfalls about 5 meters. So usually the water wheels is design, and we could imagine this. This case study proves that actually the design developed through the CFD analysis can convert up to 80% of the river's energy to electricity, and it is anywhere between the 10 kilowatts and 1 megawatt. So actually, to give you a feeling, the solar panels that we have on our roofs, it is about 4 kilowatts. So that's quite highly efficient process. But another advantage is that the simplicity of the design, the dimensions of these constructions allows simple local workers in the small countries to install it without any highly specialist skills. So it could be a win-win solution for these type of the applications. Another approach, which is actually putting us towards the flexible manufacturing, it is a flexible tooling approach. And that's where AFRC been working in the collaboration with the Ford and Gestamp and other SME companies. And the idea is actually how the same part made of different materials could be formed in the single tool. And that's the representation of the scheme, how the concept could be developed. And the last couple of slides will be dedicated to the process, very flexible, innovative, and still well unknown, and it is incremental sheet forming. So particularly this case study is actually challenging cold forming versus hot forming, and can you cold form titanium? And the answer that AFRC team gave was yes. We actually formed at the room temperature titanium parts with an overall forming depth of 100 millimeter, which was an absolutely amazing result for our partners. what it gives us, it helps actually to shorten the time to this market, because the ISF technology is very simple. You need a CNC machine, you need a forming tool, and that's actually it. You need it obviously to develop the tool path, but that could be done with a skilled technician. The next one is a reduction of the production cost and energy usage, because that's room temperature. You do not need to spend a lot of time for manufacturing of the complex dies. No material wastage, no these parameters have been associated with the process. And at the end, you obtain desirable parts in a small series, which is a requirement sometimes depending on the application. Another beautiful example how the ISF could be applied for manufacturing not only aerospace component, but for the medical application is a cranial implant. And it is obvious that we are all different, and we have different structure of our skulls. And therefore, when unfortunately the such parts like the cranial implants required, it should be individually manufactured. So it couldn't be mass production. It should be tailored for patients. And incremental sheet forming technology exactly is a process that allows you to have this flexibility. And the final sound note of my presentation is how incremental sheet forming could be applied for manufacturing of the musical instruments. This work has been done in collaboration with the Taylor trumpets and Matthew Parker trumpets. They are both trumpet manufacturers. And usually trumpet bell is a part that's manufactured manually. And you could imagine that it really depends how skillful the manufacturer, or it's just a wastage of the material. And AFRC team, with the collaboration with the Pasco Engineering, manufactured really fancy shape of the trumpet bells. And you can see one very beautiful example on the screen. So that's the approach, how we can make the different manufacturing technologies applicable for the really broad range of the components, either aerospace or medical, or even for the musical application. And to finalize my presentation for today, the very quick slide in terms of our vision and development plan. Obviously, you've heard this word from me today quite a lot. It is lightweighting, and we are working how we can develop the hybrid lightweight materials, how we can make the forming technologies flexible to make it better. Resilient UK manufacturing, the hot forming technologies, which will be on the market anyway, will be associated with the oxidation, and we are working on the development of the structures, how we can optimize the oxidation. And obviously, taking into account that the new manufacturing process are complex, we are manufacturing the complex shape parts. Tested methodologies, which gives us a classical representation of the material data, not always fully answer the questions of material applicability for the forming strategies. Therefore, we need to maintain the same pace of the development of the testing technologies as the manufacturing steps as well. And the last one, but not least, the net zero resource efficient manufacturing. And that's where we are speaking about the hybrid processes. Resource efficient manufacturing for the high strength materials, which is a requirement. We need high strengths. We are working at the highest temperatures. And obviously, if we are speaking about the hot forming process, how alternatively, how we can make the heating better. And that's me for today. Thank you very much for your attention.
Thanks, Evgenia. Hi, everyone. My name is May Hicks. I'm just going to give you an overview of incremental forming of metals at the AFRC. I sit within the Forging and Incremental Technologies team, which is very much complementary to Evgenia's team and the work that they do in the forming team. And we cover all aspects of forging and incremental forming, which covers both bulk and plate material forms. So in terms of the processes within our remit, we've got 5 primary technologies in your net shape forming, which is flow, shear and spin forming, rotary forging and radial forging. Within this, we cover a range of different material applications, including but not limited to those on the screen now, which is steels, nickel alloys, aluminium, titanium and coppers. We do also work with development alloys and new alloy applications. And these technologies are very much cross-sectoral and have applications in automotive, aerospace, energy and oil and gas, as well as others. And we do support a number of both SME partners within the UK and abroad, as well as your OEMs. So just to give you an overview of some of the technologies, so in flow and shear forming, the aim is to create near net shaped surfaces with optimum use of input material. So we've got two primary machines within the AFRC at NMIS in which we perform these technologies. So in lieu of a visit around our shop floor, here's some video footage just to show some of the processes in action. So on the left here, this is flow forming. So in flow forming, we're starting from a forged and machined preform. This is a bulk forming process. It's cold, there's no heat added other than that induced by friction. We've got 3 rollers that you can see here, which are incrementally deforming the material. So the contact point is continuously shifting. And what that means is that the material is plasticizing, it's allowed to flow, and we can achieve high deformations with much lower forming forces than you would from conventional methods. So in this process, we can achieve upwards of 200% elongation on cylindrical forms in anywhere between 20 and 80% reduction in thickness. So a key benefit of that is compared to machining, for example, a shaft type structure from solid, and there's a huge amount of material wastage. So in this process, you can get much nearer net shape. Many of the dimensional features can be left as formed, as can the surface condition, which is equivalent or better than machining in many cases. A key benefit of these types of technologies is that they are well suited to difficult to form materials that do normally require heating or very high forming forces. So because of that incremental mechanism, it can lend itself well to these difficult to form alloys. In shear and spin forming, we start from sheet or plate material. We've demonstrated anywhere up to 15 to 20 millimeters in thickness. In this process, we've got a predetermined thickness reduction with respect to the angle in which we're forming. It's a very quick process, and again is typically a good application for parts that are conventionally machined from solid or machined from forgings or multiple parts within a fabrication. So we're able to actually reduce the numbers of parts in an assembly, combining more complex features, and again achieving that near net shape surface, which requires very little post-processing after forming. On the right here, this is an example from our vertical machine. And this particular piece of equipment can create much more complex shapes due to the flexibility and the tooling setup. So the example that's actually on the right there, we're creating internal splines. So this part is starting from plate material. Now there's no preparation of this other than cutting a disc via water jet or laser cutting. So very low input preparation costs again compared to the requirement for a preform with some conventional processes. And this is incrementally forming that plate firstly over to a cylinder and then fill in that die cavity where we've got the spline features. So you can see some example components on the bottom of the slide there. So just moving on to rotary and radial forging. So our rotary forge that you can see on the left, this is quite a novel machine whereby it's got a 45-degree nutation angle, as we call it. So similar to conventional forging in that the part is located within a lower die. We've got this rotational element, but the upper die is only contacting around 30% of the surface at any one time, and that contact face is continuously shifting. So again, we're getting that reduced requirement for force, forming at much lower forming forces, but able to create much more complex features. We've also got that flexibility of the 45-degree nutation, where we can create as severe a deformation as a 90-degree flange, cold formed onto a tube structure, which would conventionally be, for example, welded onto a standard tube part. So much like some of the other technologies, we're reducing the number of parts required, reducing post-processing steps, and be able to create near net shape in a single input. Our SKK10 Radial Forge, it's quite an impressive piece of equipment because it's also in an automated cell, but what you're getting there is a close-up view of our hammers in action. So there's 4 hammers that are simultaneously deforming the material. This one is slightly different in that it can be operated cold, semi-hot and in hot conditions, depending on the level of reduction that we're targeting. It can achieve very severe levels of deformation and elongation. It's got inline induction heating within this cell, so it really does offer a turnkey solution from input billet through to forged part. A key advantage of this particular process is that you can create internal features. So you can see in some of the examples there that we've got internal splines that are being created near net shape. So for things like transmission shafts in the automotive industry, this is hugely advantageous. The internal steps on the part are also a key advantage. I mean, you can imagine these are difficult to machine, particularly on larger components, and it is a primary advantage of radial forging. So in terms of the sort of research and development work that we do, how we make it better is by understanding the process first and foremost. We've spent 7 years plus in near net shape forming at the FRC, understanding everything from raw material input and how that impacts the process, but also what the process can give us in a final part, and that's through understanding the geometric possibilities and mechanical possibilities, and then how that relates to the wider assembly of where that part would sit. A key part of our work is to bridge that gap between design and manufacture, so having enough process understanding that we can inform new part design, how to design better for these more novel technologies, and try and break that norm of inefficient legacy processes that always seem to be the baseline method to manufacture. So things like what Evgenia touched on in the method manufacture assessment, these are also where we would input the knowledge of these processes as well to get a more effective solution. So just in summary, across the processes that we've described this morning, they are near and near net shape processes. Material utilisation has improved up to 80% compared to forging and machining operations. It is a lossless process, so in terms of cost efficiency, it can be hugely beneficial. Mechanical properties are generally improved, and that's everything from fatigue, the hardness of the material, and also getting that grain refinement. So leading back to the design aspect, that's where it's particularly critical, and where we can see more benefit is by having that understanding. That could then change a part design, for example, by being able to reduce the wall thickness because we're getting that improved strength, and we can then induce more lightweighting and more efficient running costs in that part in service. And the accuracy and control of these processes is very high. It is equivalent to or better than machining in many cases. For example, in the flow and shear forming, the wall thickness controls within 0.1 of a millimetre, so there's very little machining required post-forming. So processing time overall is far reduced. It's also reduced in processing steps, so energy costs are much lower and the value stream is leaner overall. And just to give a more relevant example of how this has worked in practice, so that's the case study from one of our previous directly funded commercial projects between AFRC and Safran Landing Systems. And the aim of this was just to demonstrate flow forming as a solution for landing gear applications. So you can imagine this is quite a large scale application of this technology. These are conventionally expensive components with very high waste. But a key driving factor for this was that the long lead time. So we were looking to verify alternative routes to manufacture the landing gear. So we looked at flow forming to do that. We did a suite of experimental trials on our equipment. We have industrial scale equipment at the FRC, but we also work very closely across a number of our projects with predominantly UK-based suppliers. That really helps with that knowledge exchange aspect from design right through to the manufacturing side as well. So in this particular example, we achieved 335% elongation from the starting preform material. We achieved and validated the required proof strength in the material, and overall there was a predicted 50% in cost reduction. Now that was based on a current part design, so this is where actually working with part designers we can improve that value proposition further by starting to design parts for the near net shape technology based on the knowledge base that we have at AFRC. That's everything from me. Thank you very much.
You're on mute, Sampan.
Sorry about that. Thanks, Steph. Excellent presentation by May and Evgenia, and thank you, Stephanie, for introducing NMES. So now we move on to another presentation as well from my side. So I'm Sampan Seth, so basically a senior R&D engineer in the machining and additive manufacturing team within NMIS. So just to give you a sort of brief background, so our team within NMIS is basically under digital technologies team, and then basically we have got a mix of people with a variety of multidisciplinary skills, ranging from manufacturing engineers to R&D engineers, and people who have been in academic environment and people who have been in the industrial environment. So it's a nice blend of combination of the team, and we work on a very interesting combination of technologies, which is basically conventional and the additive manufacturing sort of team as well within the NMIS. And today what I'll do is I'll just touch base on the sort of additive side of things to make it sort of is there a better way to make that sort of webinar more useful in terms of understanding why we need additive manufacturing processes. So it's basically going to be a couple of slides from my side, just touching base on what basically our theme is and what we are really aiming forward for. So just sort of bringing things to perspective, and from the previous speakers we have heard about the forming technologies, but then now let's shift our gears towards some non-conventional disruptive technologies in which additive manufacturing is basically leading. And I just wanted to sort of touch base on the sort of timeline that what we have been seeing. So additive technologies are sort of not new into the into the current industrial applications. It's basically we understand that from sort of mid-90s onwards there was a steady increase and steady growth in terms of various manufacturing process development using additive manufacturing principles as well, and perhaps one of the reasons why there was a lot of academic push, and it was a global push towards understanding where the additive manufacturing is and where it can be really useful in terms of crossing the boundary from conventional traditional manufacturing methods to meet more complex customer demands, which started rising from sort of early 2000s, late 1990s. And the manufacturing industry, especially around heavy industry, aerospace or power generation, was basically struggling to handle as well. And there has been a sort of steady, constant growth. And one of the important highlights of developing this technology within a conventional machining team within NMIS is basically to make sure that that NMIS, the strategic goal of NMIS, lies completely matched with the current industrial demands as well. Now, this is a very interesting slide, and I would want to touch base. So additive manufacturing has been equally progressing for both metallic components and non-metallic components as well. But one of the aspects to bear in mind has been essentially in order to reduce the material waste, reduce the sort of carbon dioxide emissions, as well as improve the efficiency of the process overall. Now, we have been working on various case studies as well. So some of the bullet points which you will see, we have been working with SMEs, local SMEs, big OEMs as well, in order to sort of make the most use of their manufacturing production route, and making sure that the supply chain is meeting the complex customer demands as well. So we have undertaken a few projects, and I'll touch base on one of the applications within the EM. So how we have led to improvement in the sort of supply chain, reduction in the lead time. You don't have to store a lot of feedstock material, or don't have to operate on large feedstock material. And of course, that effectively describes how cost effective your operations would be as well. And also from more technical point of view, I mean, as compared to conventional manufacturing or conventional subtractive manufacturing technologies, that how we are improving on the functional capabilities of certain components by not only enhancing their parent properties, but also providing them additional functionality if that is needed as well. And one of the key factors as well is that the advantage of the technology, or the beauty of the technology, lies in the fact that there is a design freedom, of course, that comes with the constraints of each process. So when we talk about system, process, material, so there is basically design rules which are basically made around each of the AM technologies, and NMES is basically working within our team as well. So there are design for additive manufacturing people who are working there, and basically we are working on improving the possibility of attaining complex design, complex use cases for industrial applications as well. Now that brings a very sort of interesting comparison and of the sort of comparison of conventional versus sort of advanced or additive manufacturing, especially. So there has been a lot of case studies. We have been involved or rather there are a few running projects which are ongoing within our team, and there have been projects which we have delivered, and we have basically try to address one of the problems, or rather one of the challenges with a lot of people have questions about, and the adoption of additive within their production routine, is how effective the process is, and basically how effective it is in terms of maintaining economics, as well as the least impact on the environment as well. So just for a quick reference example, so there are two approaches that we can use to fabricate this component. Either we start with a conventional manufacturing using a block or an ingot of material, or we rather use a material based on the material compatibility, and we use the additive layer manufacturing techniques to build this up. Now there is a sort of generic comparison that's usually been added to a traditional and additive manufacturing techniques, as that we can have better design, we can have a more sustainable process. That means from this route, what we generally see is that the buy to fly ratio, of what we call as the material which is being removed to attain a certain geometrical requirement of a component, is extremely high as compared to additive manufacturing route. However, it doesn't suggest that there is not really a specific balance of each of the process, and that's a very interesting topic which I'll touch base on in a couple of later slides as well. And what that also brings about to the OEMs as well as the SMEs is that it gives a capability of distributive manufacturing advantage, as well as over the conventional manufacturing techniques, is that it's not centralized, that we can formulate, or we can form parts which are sort of more customer demand specific parts, as well as rather than having a batch production which is centralized and then it is distributed to the customers. Now it's equally important to highlight the fact that there have been a lot of work there, and we know from the growing market trends that additive manufacturing will have enormous effect on the global manufacturing market, global production market as well. And if the reports, basically what you are seeing is, so there's going to be a significant increase in the overall adoption of AM within the manufacturing market about between 2025 and 2030. And this also brings us to a very sort of challenging point as well, in sort of lowering the global emissions as well. Now, one of the important aspects to highlight is within the conventional as well as the additive manufacturing processes, is that how energy heavy, how carbon dioxide heavy some of the processes are, and how the AM, the principles of AM, which basically are able to lower the emissions. So most of the industries which are heavy on steels, or non-ferrous alloys, or aluminium, or plastic industries, or even construction industry, there is a significant increase in the overall carbon dioxide emissions from the industry, and how that can be brought down to about 40%, and how the AM has got potential. So basically applying AM across various industries could reduce, because of how the process are basically reducing the overall feedstock requirement. The sort of reuse, the word remanufacturing is something that we are hearing a lot, as well as the word hybrid that we are hearing a lot, how effective that process becomes in terms of lowering those emission values, and even maintaining the economics of the process as well, that there is no economic disadvantage of the process as compared to the conventional one. Not suggesting that one is better than the other, but of course, yes, creating a massive potential as a disruptive technology. Now, that is the sort of background on, where I would say the NMIS sort of focuses on moving forward. And one of the important things to highlight is that we work very closely with one of our tier 2 members, Hybrid Manufacturing Technologies, and we have developed within NMIS. So we have got a hybrid AM process, which is basically a combination of additive and subtractive technology, and it's a unique process that basically that is synergistic interaction of the conventional machining operations as well as the additive manufacturing process as well. And what it basically does is, and we are currently working on various projects on that, and basically what it does is it allows a sort of single clamping system or a single clamping operation that will cover both subtractive as well as additive manufacturing. That means it helps a lot overall in moving equipment or moving the component workpiece around the workshop as well. It immensely reduces the material waste, which is again one of the aspects which I touched on previous slides as well, that how the process or the AM process could improve a lot in terms of feedstock waste, as well as ease of manufacturing by reducing the overall process time as well as fabricating components which are pretty complex and even require lesser lead times as well. So that's a very unique nature that we are currently working within our hybrid AM process within our group, and basically that also details out that how important it is to have people with the background in conventional manufacturing as well as people in the background of additive manufacturing to answer these questions. Now, in order to move in terms of the case study, and so we did a project, Innovate UK project, and basically what it was is repairing or localized repair of a forging die, basically from one of our OEM partners. And what we did, or what we displayed in the project, was that a complete remanufacturing cycle, that we got a die which was absolutely worn. There were flash lands worn out. There was the cavity side of which was worn out as well. So what we did was we did the deposition, and then we did the final finishing to restore the component, not only in terms of the geometric tolerance, but also improving the functional quality of the surface as well. So basically we applied a hard face coating on an existing component, which basically in service life increased the service life to 108% from the parent material, and also reducing the overall CO2 footprint as well. That if this was supposed to be rejected, that basically that's basically a new material altogether, a new product altogether that needs to fit in. And basically that process is very efficient in terms of energy as well as cost. The other advantage that I would want to highlight, that we in terms of case study, that as a team that we are working on, is feature addition on certain components, which again becomes quite challenging using traditional manufacturing methods. The case study, or rather this was a PhD case study that's been concluded within our team, is one of the titanium alloys as well. So we were planning to add a feature on the existing landing gear, basically. And basically what this showed is that our process is capable of adding features as well. So effectively reducing a lot of machining time and improving the overall process economics, as well as overall a reduction in the carbon dioxide emission. Now, just to touch base on some of the important highlights of our group, as well as what essentially we are capable of doing, as well as within our group. So we are capable of a full remanufacturing cycle, that if we have the capabilities, and this is a lot of projects which are ongoing within the group, that we take a component which is worn, we clean the component, we do sort of reconditioning using some of the processes so laser metal deposition that we touched on. We have got a wire arc additive manufacturing process. This is going to be a new addition, which is essentially a solid state AM process, a high pressure cold spray process, and the other one is again a solid state process of friction stir. So combining or using individual techniques and following the sort of value stream of the remanufacturing, we have shown that effective use of conventional manufacturing combined with additive techniques as well, how cost effective and how sort of environment friendly those processes could be. I think that will be all from my side, and feel free to ask any questions, or do you have any questions? I'm more than happy to answer.
Thank you very much to all the speakers today. So the question and answer session is open for a very brief moment in time, as we've only got a couple of minutes left today. So if there are any questions, please feel free to either raise your hand, or you can pop them in the chat box or the Q&A. So is there any questions just now? No? Great. Just a couple of ones just from myself, guys. Again, you were speaking a lot around the method of manufacturing methodology. Can that be applied to non-metallic components as well as metallic?
Absolutely. Absolutely, yes. That's the beauty of this process, and the flexibility of this process is either could be done on the very high level or in depth, or actually, if you would like to compare absolutely different categories of the materials. We here in AFRC have another specialization center, which is lightweight manufacturing center, and it is specialized on the composite material. But these days, we also have inquiries about the polymers and polyethylenes. And actually, as soon as we know what type of the materials you would like to change between each other. So for example, like in the Ford example, it was between the steel, aluminum, and composite. You obviously need to know what are the materials and what are their capabilities, and potentially develop a new manufacturing routes for each of them, or the hybrid one. So the direct answer to your question is yes. And obviously the more detailed is basically we need to be aware about the specialism of the material. What are the formability, what are the restrictions, temperature requirements, and obviously the process requirements as well. But that's certainly what we can do using the expertise of the overall NMIS team.
Brilliant. And May, you're speaking a lot about having the processes available on site. So how do you then get the processes developed and put into industry for your incremental side?
So this is really dependent on the part, how mature that part design is, whether it's a current part, a new part, and also what process we're talking about. But just to give a bit of a flavour, so we've got a couple of options, but one of those is to work directly on site with our supply chain partners. So it's been able to create that connection between the suppliers that exist, while upskilling them to be able to adopt, the novel techniques that we're developing, and sort of tying that in with the OEMs. We really are strong in supporting that sort of TRL 4 to 6 range and getting a process to be production ready. And what we want to be able to hand over at that point is then, something that with minor refinements is basically ready to go. We have an example whereby we had a 3-year project, AFRC. We developed a novel technique. The final stage of that, we physically took our tooling on a 7-year-old machine and took it to a 70-year-old machine, and we're able to create a like-for-like process. So we're actually doing that physical transfer, being there on site with the suppliers, their understanding, you know, when we change these parameters, this is what's happening, why, because we're able to embed that knowledge. And I think that really gives the supply chain that sort of skill to really get up and running. They've got the history, they've got the knowledge. And it also means that for new parts where perhaps the supply chain is less mature, we can help develop that. If the supply chain is mature and it's a new application, we can supply a technical pack, you know, everything's then like for like and can be transferred. But I think the key message is we will work to bridge that gap. And I think that is our key aim within AFRC, is, you know, to bridge that gap between academia and industry and actually enable our customers to have the impact and able to go out there and actually productionize whatever we've developed in the centre.
That's so true. Thank you very much. Laura, that seems to be all from the question side.
No problem at all. Thank you everybody for attending today. Our next event is on Thursday the 7th of October with our electrification experts. So please do sign up for that event if you're interested. I'll just pop a link in the chat area. Okay, thank you to all our speakers today. I'm just going to end the session now.